Right, so now we continue with Chapter 7, Work and Energy. In the previous video, we covered point A and B, and now what we're going to look at is deriving an expression for the work done by a varying force. So we're going to shift our focus onto work done by varying forces. Up until now, we only considered the case when the force is constant. So here we have a plot of force being applied as a function of displacement on the x-axis. And what you'll notice is that the force is not constant with displacement, but it varies. This line isn't straight, but in fact it's, a curve. And we also need to realize that the area under a force displacement curve is work. And the reason for that is because force multiplied by displacement gives work, right? So if we would like to calculate the work done by this varying force, its equivalent problem, an equivalent problem is for us to calculate the area under the curve, and then that will give us the work. When it comes to calculating this area, the way we're going to do it is we're going to divide the area into individual sections where the force is constant, and then sum up all these sections. Another way of thinking about that is we're going to divide this area into a number of little blocks, and then what we're going to do is calculate the area of each of these little blocks, and then add up all of the area of each of the blocks to get the total area. You can see what we have here is a little block. Each block has width delta x, and it has a height given by f of x, sort of the y value of this curve for that specific block. So the area of this little block is going to be given by f of x delta x. When it comes to calculating the total work done, you can see the amount of work done for one given section is going to be given by fx, it's the y value on the graph, multiplied by the width of this little box. And the total work performed is given by this expression here, where we make use of the summation sign. So this summation sign is telling us to add all the little blocks starting at xi and ending at xf. So add all the little blocks whose area we calculate. You can see in our example we wanted to calculate the area from xi to xf. So that's why we sum in over that specific domain. More in a precise form, we want the limit of delta x to tend to 0. And this notation is something that we saw before when we were dealing with derivatives. And the reason why we want this delta x to tend to 0 is we want these little blocks to be as narrow as possible. And by doing that, it gives us a more accurate answer. And this in fact then gives us this notation here, which refers to the integral. So adding up all the blocks in the limit is equivalent to calculating the integral. So therefore we can express the work done by fx on the system of particles as it moves from xi to xf as the work is equal to, we read this as the integral from xi to xf of fx dx. So it's the integral of the force over the domain from xi to xf with respect to dx. So I've spoken about how important it is for us to calculate the area under the curve in order to determine the work, and I've used the word integration. And integration is a tool that we use in physics to calculate areas, and in fact it's a topic that you'll cover in in great detail in maths. But for me, it's interesting to just sort of teach you a little bit about integration and give you the background so that you're able to use it as a tool for the physics that we want to do. So in this sheet, what I have here is we're going to consider a function. So for example, the function might be 3x squared. And then we know what we can do is, we can differentiate the function, right? And we're all familiar with how to differentiate a function. We simply take the 2 and we multiply it by the 3. It gives us 6, and then we decrease the power by 1. But when we speak about integration, we're speaking about how do you go backwards. If you're already given a derivative, how do you go backwards and determine what the function is? In that sense, we might think of differentiation. We might think of it as an integration. We given some derivative and we want to go back. So how could we go back from 6x to 3x squared? Well, let's take a look at another example. If I'm given a derivative and the derivative is 18x squared, as shown here, then the question is, how can I go back from this derivative and find the original function? And there's a little recipe that we follow which tells us how to go back and integrate, how to undifferentiate. So the rule that we take is we start by having the x. We take this power. At the moment the power is 2. The rule is that we raise the power by 1, so we increase it by 1. So if we go from 2 to increase 2 by 1 gives us 3. And then what we need to do is take this number in front and we need to divide it by the new power. So the new power that we found over here is 3. So this then gives us 18 divided by 3 is 6, 6x to the 3. We can check if we've performed the integration correctly, and the very simple way for us to check is by differentiating this. If I differentiate this, it becomes 6 times 3 is 18 x squared. So this shows that we have performed the operation correctly. We've performed the integration correctly. Let's have a look at another example. If we want to take the function 36x to the power of 3 and we want to integrate that, then I start off by writing the x, and at this time the power is 3. So now remember, I need to increase this power by 1, so I change the 3 to a 4, and then I need to divide the number 36. I need to divide that by the new power. The new power is 4. And if we simplify this, then we can see 36 divided by 4 is equal to 9x to the power of 4. And if we differentiate 9x to the power of 4, we do indeed get 36 to the power of 3. So this goes to show that our integration has been successful. An interesting case we might have is if we have the number 5. So if we're given that the derivative of a graph is 5, and we asked to integrate that and find what the original function is, then at first that might seem a little bit confusing because we don't see an x there. But we can actually take this 5 and write it as 5x to the power of 0, because remember, anything to the power of 0 is 1. So by writing 5x to the power of 0, it's of course just 5. And if we integrate 5x to the power of 0 and we carry out the same rule, then the rule says we start with with the x, we raise the power by 1, so we make this from 0 to 1, and then we take the number in front, we take the 5, and we divide it by the new power. So then this just gives us 5x. And we can see that basically, having done this, if we differentiate 5x, of course this just becomes 5. So that's again a way to check that we've done it correctly. If we have a function with multiple terms, as in here we have 26x plus 6, then we do it in exactly the same way, except we just do each of the terms individually. So when we deal with the 26, then, you know, at the moment it's 26x, so it's x to the power of 1, so we change this to x squared, and then we take our 26, we take our 26, and we divide it by the new power, so the new power is 2. Then we need to also take care of the second term. So remember, 6 is the same as 6x to the power of 0. So if I want to integrate x to the power of 0, then I make it x to the power of 1. And of course, it's just going to be 6 divided by 1, which gives us the 6. So this then is equivalent to 13x squared plus 6x. And if we differentiate this, you know, we get 26x plus 6, which shows that we've done our integration correctly. So then, in the next slide, we generalize this rule. We give, in this slide, the general mathematical notation. So if we have a function f prime of x, you know, this is the derivative and it's written in this form, ax to the n. If we want to go back and we want to find out what the function itself is, so remember the function is just f of x, then the way we do that is we take the power of the derivative and we increase it by 1. So then we have x to the power of n plus 1, and the coefficient, we divide the a by the new power, so it's divided by n plus 1. So this statement here is just a general mathematical rule of writing out the recipe that we've been following to do our integration, to perform these steps. So we've been looking at integration and we've seen that there's a little rule or recipe that we follow to perform integration, but it's super important for us to remind ourselves of why we want to do integration and what we're hoping to achieve. And this is summarized in this picture here. So remember, when we deal with differentiation, differentiation refers to a gradient. So what I have here is some function f of x given by this varying black line. If I differentiate f of x, then I get f prime of x, which is a gradient at some point. If I differentiate, the opposite of differentiation is integration. And integration is a tool that we use to calculate an area under a curve. So if I wanted to calculate the area from, you know, between a and b under this curve f of x, under the curve f of x, then I would use integration to find this area. And the integral I would need to evaluate is the integral from a to b of f of x dx. So we've seen the rule, the recipe to follow for integration, but now it will be interesting for us just to look at an example to confirm that this recipe or this rule actually works and that integration works as we think it should. So here's an example then. Find the area under the curve between x equals to 0 and x equals to 3. So in this example, you can see what I have is a curve, and this curve is given by f of x is equal to 2x. And you can see it's f of x is equal to 2x, because when x is 1, f of x or y is 2. When x is 2, f of x is 4, and so forth. But the problem we asked is to find the area under this curve between x equals 0, so from here, and x equals 3. So if we look at this, then this actually forms, a triangle. This forms a triangle. So the question is, find the area of this triangle, the area under the curve between x equals to 0 and x equals to 3. And what we're going to do is we're going to use first the conventional way to find the area of a triangle, and secondly we're going to use the integration method. And then we're going to compare the two answers we get, and hopefully we'll see, the answers will be the same, to show that our integration method works well. So a formula that we often use to find the area of a triangle, the area of a triangle is just half base times height. So for us, the base is 3, so the area is going to be half times the base is this base here, the length is 3, and the height we can see is 6. So it's half 3 times 6, and this is equal to 9. So according to this conventional formula, the area of this triangle A is equal to 9. Now let's try use our integration tool and see if we can get the same answer. So here we've written this question in words. We've written it in integration formula. The area is equal to the integral from 0 to 3 of the function 2x in terms of dx. If we perform this integration, then what we're integrating is 2x, right? So the rule that we do is we take the x, and at the moment it's x to the power of 1, so we need to increase the power by 1, so we make that a 2, and then we take this old coefficients and we divide it by the new power, so divide by 2. And the notation that we use is we rewrite this integral sign, and we say that this is over the domain from 0 to 3. So in the next step, what we can do is we can simply just simplify this expression inside the brackets. So this is just going to be x squared, and as x goes from 0 to 3. Now, the way we finish the problem, or the way we evaluate the problem, is we take this x squared and we substitute the top number, the 3, in. So this becomes 3 squared, and then we put a minus sign, and then we substitute the 0 in again. So wherever we see x, we put a 0. So this is just going to be 0 squared. And we can see that, 3 squared minus 0 squared is also 9. And what we see is that using both of the methods, we arrive at the answer 9. So this is a confirmation then that our integration tool, our integration recipe is working correctly, because it gives the correct answer. It gives us the answer that we were expecting. In the slides then there's another example we can look at. In this example, we asked to integrate 9x squared, that's our function, between the limits of a and b. And the way we do that is, as before, we take this power and we increase it to 1, so it becomes x to the power of 3, and then we take the 9 and we divide it by the new coefficient, and then we write the limits as shown. So this simplifies just to 3x to the power of 3, and this is between the integration bounds of b and a. As I've already said, the way we evaluate this is first, wherever we see a x, we substitute b in. So this becomes 3b to the power of 3. And then from that we subtract, wherever we see an x, we put an a in. So it's minus 3a to the power of 3. And that's our solution. Right, so then this is a sufficient introduction to integration to show you how it works, to show you how the area under a curve can be calculated, and from now on we'll move forward and use this, apply it as a tool. Right, so now we move on to look at Hooke's law, and Hooke's law deals with the case where a spring is connected to a block. So the situation is we'll have a block of mass m, and it's connected to a spring, which is in turn connected to the wall. And then along with this we have some concept of the distance x, which is the current position of the block. So taking a look again then at Hooke's law, the force of the spring on the block is given by F subscript s is equal to minus kx. This s is used to denote that it's the force of the spring, and k is the spring constant. It has units of Newton per meter. X is the position of the block relative to its equilibrium position of x equals to 0. Just to note that the spring constant indicates the stiffness of the spring. So if it's a very stiff spring, if it's a tight spring, then k is going to be a big number, a large number. If it's a very loose, loose spring, then k is going to be a small number. X may be positive or negative depending on the position of the block. If we take a look at this picture, then we can see, with the block on the right hand side of the x-axis relative to its rest position, we would have x being a positive value, whereas in figure C we have x on the left hand side. So in this case x is going to be a negative value. Here we have Hooke's law, Fs is equal to minus kx. When x is positive and the spring is stretched, the spring force is directed to the left. So in this case we have the force acting to the left. It's going to be, pulling the block back this way towards the 0 position. When x is 0, the block has returned to its natural position. The force in this case is 0. There's going to be no force on the block, and you can see that by substituting 0 in there, then you get Fs is equals to 0. Of course, if the block had been in this position and it had been let go, then as it moves to the left, it would be speeding up, it would be moving faster. So this means that when it arrives at this point here, even though the force is 0, it's going to have some kinetic energy, and this kinetic energy is going to keep it moving towards the left, and as it moves, the spring is going to be slowing it down until perhaps it comes to a stop. On this side, when x is negative, the spring, we have a compressed spring, and the spring force is to the right. Again, it's pushing it to the right. So the block would have moved from this position, it would have moved to the left, eventually it would have stopped, and then the spring force will be pushing it to the right again, as shown in this picture here. we speak about a restoring force. So a spring force is a restoring force in the sense that it's always trying to restore the block to its zero position. It's always acting towards the zero position. And here you can see the importance of this minus sign in Hooke's law. The minus sign ensures that the force is always acting towards the center, right? When x is positive, then Fs is going to be minus k times a positive number will be a negative number. So it means that the force of the spring is pointing to the left. When when the block finds itself on the left hand side of the zero position, x is going to be a negative value. In this case, we're going to have minus k times minus x, and this is going to give a positive overall value for Fs, and we have the force pointing towards the middle of back towards the origin. The work done by the spring force on the block as it moves from minus x max to 0 is the area of the shaded triangle. This is half kx squared, and we're going to in fact derive this. Let's take a look then at an example where you're asked to calculate the work done by a spring as a block for a block where it's released from some position minus x max, and then it moves to a position 0. Remember, we asked to here calculate the work done by the spring. So the work done by the spring is equal to, in terms of our definition of work, it's the integral of Fs dot dr, and this follows by the definition for the work done by a non-constant force. So if we go on to evaluate this, from Hooke's law, we know that Fs is equal to minus kx in the I hat direction, and the displacement vector dr, we can write this as dx in the I hat direction. We interested in integrating this between some bounds xi and xf. Of course, we can note that these bounds are, the starting position xi is minus x max, and the final position is 0. So that's where these two numbers come from. You can see this line over here deals with the dot product. We asked to calculate the dot product between these two quantities in brackets. In fact, if we dot the vector I hat with the vector I hat, then we get 1 times 1, which is the length of each of the I hats, and the angle between them is 0, so we just given 1. So this means that when we compute this dot product, it just comes out to be minus kx dx integrated between these bounds as discussed. When we want to integrate minus kx, then remember the way we do that is we increase the power by 1, so it becomes now 2, and then we divide the minus 1 by the new power. So that's where this minus half comes from. As before, we write our integration bounds as shown. When it comes to evaluating this integral, we first substitute the 0 in. Wherever we see an x, we write a 0. So this gives us half k times 0 squared minus, now what we do is wherever we see an x, we write minus x max. So this is then minus half kx times minus x max squared. When we look at this, you can see that the first term is simply going to be 0, and this minus multiplied by this minus is going to give us a positive. This is minus x max squared, so it's also going to be positive. So the solution that we left with then is half k x max squared. So this is then the work done by the spring as the block moves from minus x max to 0 is given by half x max squared. The question or the problem could have been phrased slightly differently, in that we could have been given different starting and ending positions. Perhaps we could have been told that the block started at 0 and then it moved to position x max, right? And we would have solved that problem in exactly the same way, except we would have used different integration bounds. We would have taken care to use the precise start and end position of the block, and that in turn would have given us a different solution. This next slide illustrates that fact, where for arbitrary displacement, for an arbitrary displacement from position x equals xi to x equal xf, the work done by a spring is given by this expression, where, as I said before, the bounds are now from xi to xf, and we need to integrate this function, and performing the integration in a similar way to which we've just done gives this expression here. You can see we had something very similar in our example. These steps that we followed up until this point brought us to this expression here, where we have our integration bounds from minus x max to 0. In this case, we have a very similar expression, the same expression, with different integration bounds. So what I'd like you to do yourself is to perform this integral and just make sure that you end up and satisfy yourself that you can end up with this result shown here. So what we're going to be looking at next is kinetic energy in the work energy theorem. So what we have here is a block of mass m, and the block is being acted on by some forces, perhaps a number of different forces. And the block has an initial velocity of vi, but because of these velocities, it has these forces, it has some final velocity of vf, which isn't the same. And you can also see that in this case, the block has undergone some displacement of by distance delta x. When we speak about kinetic energy, we define that as half mv squared. And for kinetic energy, we're writing it as a capital K. So cap K represents kinetic energy. At this point over here, it would have kinetic energy of half mvi squared. At this point, after the forces have acted on it and it's in a new position, it will have kinetic energy of half mvf squared. Bringing us to the work energy theorem, we see that the work done by the external force is equal to the final kinetic energy minus the initial kinetic energy, or the change in the kinetic energy. And expressed in words, when work is done on a system and the only change in the system is its speed, the net work done on the system equals the change in the kinetic energy of the system, as expressed in this equation here. So this then is the work energy theorem. One of the things you may be asked to do is to derive the work energy theorem. So this over here is the definition that the work energy theorem that we're looking to derive, the equation that we're looking to derive. And again, the situation that we're dealing with is the one that we discussed before, with these forces being applied to this block and it's changing its velocity. So then the derivation I've written out here, consider a constant force displacing a mass m over a distance of s meters. What we can do is, firstly, we can apply Newton's law, and simply in the x direction that will be given by equation 1. The second thing we can do is we can look at the work being done. And if we look at the work being done, this is the definition. And remember, what we have then is we have the force times the distance. ds will be the distance. It's operating over distance with respect to x as the block moves from 0 to s. So the work will be F times S. Perhaps you can see this very simply because we just have a block moving a distance S. The work is going to be F times S. So substituting equation 1 in equation 2, then we can see that, or substituting equation 1 in equation 2, we can see that the work is going to be given by mass times acceleration times s. We can also use the equations of motion to get to continue with the derivation. So the one equation we're going to use is that the acceleration is v minus u over t. This is just a reworking of the equation v is equal to u plus at. We've rearranged this equation to make a the subject of the equation. We have this second equation where the distance is going to be half v plus ut. So here in 5 and 6 we have from the equations of motion an expression for a and an expression for s. And what we're going to do is we're going to substitute in equation 4, where we also have an a and an s. We're going to substitute equation 5 and equation 6 in for a and s, and then this brings us to work is equal to mass times, here we've rewritten the a by v minus u over t, and here we've rewritten the s by half of v plus u times t. Then we can simply multiply these terms out. If you want a quick way to multiply it out, you'll notice that this is the difference of squares, right? This is v minus u times v plus u. So it's the difference of squares. Is multiplying these two terms out will simply give v squared minus u squared. And then, the t terms will cancel out. There's a t at the bottom and a t at the top. And we'll have a half, factor of half remaining, as well as a factor of m remaining. So our expression then is the work is equals to half mv squared minus half mu squared. You'll remember before that on a previous equation we said that whenever we see something in the form of half mv squared, that this relates to kinetic energy. So what we do is we make use of that fact. You can see that here we have half mv squared minus half mu squared. So half mv squared is the kinetic energy of the system. So this is going to, half mv squared will relate to the final kinetic energy. Half mu squared will relate to the initial kinetic energy. And whenever we have something in the form of a final minus initial, we write that as a change. So we end up with then that the work is the change in the kinetic energy, which is the work energy theorem. So here we give an example where a 5 kilogram block, it slides over a horizontal frictionless table with velocity of 1.2 meters per second, and it is stopped by colliding with the spring. And we asked to calculate by how much is the spring compressed, and we're given that the spring constant k is equal to 1.5 times 10 to the plus 3 newtons per meter. So as we start this problem, it's always good for us to make a sketch to illustrate what's happening. So we have our block and it's got mass m. We're not given its mass, but we're told that it's moving at 1.2 meters per second squared initially, and it's sliding along this frictionless table. Then it collides with a spring. The spring constant is given to us as 1,500 newtons per meter, and then eventually it comes to a stop. By doing so, it's compressed the spring, and by coming to a stop, it will have a final velocity of Vf equals to 0. And what we asked to calculate is by how much will the spring be compressed. So in terms of our figure, the amounts that the spring will be compressed, this is this little amount here, x, that I've indicated. The spring will be compressed relative to its position at 0. And the way we're going to solve this this problem is by using the last two concepts that we've sort of derived. The first is the work energy theorem, and the second concept is the work, the work for a spring is given by this expression half kx squared. So first then, applying the work energy theorem, you can see the work energy theorem says that the work done on the spring will be the change in the kinetic energy. So this will be, whenever we have change in kinetic energy, it will be the final kinetic energy minus the initial kinetic energy. If we have a look at the values, the final speed is going to be 0 because the block is going to come to a stop. So this will be half. We're not given the mass, but it will be half times the velocity. The final velocity will be 0 squared. The final velocity will be 0 squared. And then what we need to do is subtract the initial kinetic energy. The initial kinetic energy will be half m, and the initial velocity will be vi squared. We actually given that value. So then this is going to be equals to let's see, it's going to be minus a half mvi squared. We also know that the work is given by minus half kx squared. This is going to be the work for the spring. So here we've seen that the work is half mvf squared, and here we see it's half mvi squared. So thus we can say, we can take this and we can equate the two. We can equate half mvi squared, we can equate that to half kx squared. So we have minus half mvi squared is equal to minus half kx squared. Remember, what we're trying to solve for is x. What we're trying to solve for is x. So we can take this expression and then we can rearrange it. So you can see that the minus halves are going to cancel out, and then what we're going to have on this side is we're going to have m, and we're going to have divided by k times v squared is equals to x squared. So this means x is going to be equal to the square roots of m over k times v squared. It's going to be the square root of everything, right? So this is going to be equal to m over k times v r. And now what we can do is simply substitute the values in. I see, in fact, we are given the mass of the block. It's given as 5 kg, so we can substitute that in. We also given the spring constant is 1500 and the final velocity. So substituting the different values in, then we'll have the square root of 5 over 1500, the square root, times VI, the initial speed is it's given as 1.2. And if we calculate what that is, that calculates out to give us 0.069 meters, which is of course equals to 6.9 centimeters. Power is the rate at which work is done. The average power is defined as the amount of work that's been done divided by the amount of time that's elapsed. You'll remember that previously when we looked at quantities such as velocity, we had average velocity, and then for us to define instantaneous velocity, we took a limit. So in a similar way, we define the instantaneous power as the limit as this time interval over which the work is done tends to 0. And we know that whenever we take a limit in this form, this gives us a derivative. So the instantaneous power is the derivative of the work with respect to time. We know that work and energy, they both have units of joules, and obviously time has units of seconds. So for power, the unit is joules per second, or also referred to as watts. We can also, rearrange this equation if we need to calculate the amount of work being done from the power. There's this interesting case where we can express power in terms of a force when the force is constant. And we can see that by, rewriting the definitions. Previously we saw that the instantaneous power is the derivative of the work done with respect to time. We've already seen that the work done is the dot product between the force and the displacement vector. So next what we can do is we can, distribute the derivative and break it into two terms. So we have df dt dotted with ds, and we have f times ds dt. If we look at these two terms individually, the first term shown here, we're dealing with the case where the force is constant. So because the force is constant, we're dealing with a case where df dt will be 0. So that means that this whole first term will be 0 as a consequence of df dt being 0. The second term, we have the force dotted with ds dt. We know ds dt is actually velocity, right? The change in displacement with time is velocity. So we get this interesting result where power can be rewritten as the dot product between the force and the velocity, and this specifically applies to the case where the force being applied is constant, which allowed this df dt term to be 0 and this whole first term to fall away. We end this chapter with an example where they speak of a car that has a power of 75 kilowatt hours, and it's traveling forward with a constant speed of 100 kilometers per hour, and we asked to calculate what is the forward propulsion force delivered by the engine. I'm going to leave this last problem as a problem for you to solve yourself. The answer is given here. It's a relatively simple problem to solve. What you will do is you'll make use of this equation here that we've just derived. The power is the dot product between the force and the velocity. You can use that equation to solve this problem. One thing you may need to take care of is to convert this 100 kilometers per hour, you'll need to convert that into SI units of meters per second, and then apply this equation that we've just derived. Good luck with that simple problem.